Hello. I have been studying Richard McElreath's Statistical Rethinking, which is a very good book, but on page 85 there is a piece of code that is fairly inscrutable, and I spent quite a while deciphering exactly what it is and how it works. So I thought I would make a video about it to save you some of that effort. So the code on page 85 is called R code 4.16. It's extremely dense. Multiple programming tricks, multiple mathematics tricks going on. So first, there's some background you need. The code refers to D2 $height, and you need to know what that is in order to understand what the code's doing. So the first thing is you have to install the Rethinking module that Richard McElreath wrote for his book. And then you have to tell your R session, I'm going to be using the Rethinking module. And then you need to tell your R session, I'm going to be using a data set that's built in called Howl1. Then you can actually take the Howl1 data set and assign it to a variable that he calls D. This is what we call a data frame in R. It's columns that can each be different sorts of things. Height, weight, age, and male are the 4 columns in this data set, and every row is person. He doesn't want to take the entire data set. He wants to only take the adults and talk about how tall they are. So how do we select just the adults? That's what this line does. D2 is getting assigned a part of the data frame that satisfies this condition on the rows and this condition on the columns. Since there's nothing here after the comma, then that means we're taking all of the columns. But we're not taking all of the rows, we're only taking the rows that have an age attribute greater than or equal to 18. So this is how we say, let's just take the adults from data frame D. So every row is a person, every column is a variable, and D2 has ages that are only 18 or above. That's the background you need. Now we can get to the actual code itself. The first couple of lines are fairly straightforward if you have any experience with coding in basically any language. Mu.list is getting assigned a sequence of numbers from 150 to 160, 100 numbers long. Now, it's a bit of a fence post error. If you'd said 101 numbers, then it would have been 150, 150.1, 150.2 exactly. Because there's 100 numbers, there's going to be some messy decimals. So 150, 150.1-ish, 150.2-ish, and so forth. Likewise, the sigma list is going to get assigned a sequence from 7 to 9, length 100. So there's 100 numbers from 7 to 9, so there's 50 per number. So 7.02, 7.04-ish, etc. So that's 2 lists of 100 numbers. And then there's this command expand.grid, which combines these 2 vectors. So you might think it's making a 100 by 100 matrix of some sort. No. It is making a data frame with 2 columns and 10,000 rows. So you're taking the first entry is the mu, so it's going to cycle through all the values in the mu list first. So it's going to take the first value of sigma 7 and do 157, 150.17, 150.27, etc. Then once it finishes that, gets up to 167, it will then go to 7.02 and do 157.02, 150.17.02, etc. And there will be 10,000 of these rows with 2 numbers each. That is getting assigned to post, which is short for posterior. He's constructing the posterior distribution. So first, this is the list of all the candidates for mean and sigma combinations he wants to look at. Now we come to the really complicated line in the code. Post $LL gets assigned sapply 1 nrow post function I sum d norm d2 $height post $mu I post $sigma I log equals true. What on earth is all of that? It's going to take a while, but let's break it down. First of all, the post data frame so far consists of a column labeled mu and a column labeled sigma with combinations like 157, 150.1-ish 7, etc. And then we're saying post $LL, that's posterior log likelihood is what it stands for, And it's saying that we're going to create an LL column. So we're adding to the data frame and assigning it this mess. sapply is saying we're going to apply this function sum to a bunch of quantities here. Let's break this down. The first thing is 1 to n row post. N row post is the number of rows in post, 10,000. So this is saying 1 to 10,000. And then it's saying function I, which means the I is going to be the 1 to 10,000. I is going to count through from 1 to 10,000. The sum is going to be applied to all of these quantities. So let's see what this is actually doing. This is the dnorm function, which is the density for a normal distribution. So it's actually going to give the height, not the area like we often encounter, but it's actually going to give the height of the function. I'll get to why we're doing that in a minute. For every row in post, there's a mu and a sigma labeled by I. We're going to take that mu and that sigma, and then we're going to take every value of height in our data set, and we're going to plug those in as x values and say how tall is the bell curve at that place. And then we're going to take the logarithm of that quantity, and then we're going to take all those numbers and add them up. This dnorm fed a vector is going to give a vector of the heights of all of these things, or the logs of their heights. And then the sum is going to turn it all into one number. The sum of the logs of the densities. All of that is one number, and then we're going to do that 10,000 times. We're going to get the log likelihood for every value of mu and sigma given that entire data set. That's what we're doing. Now, a reminder on likelihood. In the discrete case, likelihood is the probability of getting one data point times the probability of getting the next data point times etc. That giant product is the probability of getting all of your data, given your assumptions. In the continuous case, instead of multiplying actual probabilities, we're multiplying probability densities. And for every data point, there's going to be a density. So you multiply them all together and you get the likelihood. Why are we doing the logarithm? If you take the logarithm of the likelihood being a product of all these densities, the laws of logarithms say you can split that up into a sum. So if you found probability density for one data point, and you took its logarithm, and you added them all up, you would get the logarithm of the likelihood, the log likelihood. And that's exactly what this code does. Dnorm gives us that height, that probability density, the density of the normal distribution. We're going through this 10,000 times. We're taking each row of post, we're taking its mu and its sigma, and then for each of those rows, we're going to take all of the data, calculate how high they are, take the logarithm, and then add them all up into one number, the log of the likelihood of getting all of those data given this particular value of mu and sigma. So he calls that variable LL because it is the log likelihood. Now we come to the second to last line in that piece of code. Post $product gets assigned the post $log likelihood plus dnorm this plus d uniform that. Reminder on the Bayes that we're overall doing here. If D stands for the data and M stands for your model, the basic Bayesian formula is the probability of your model being true given your data is the probability of the data being true given your model, which was standard probability, times the probability of the model divided by the probability of the data. And that last one we have no idea how to do generally, but we don't need to. Right now we're talking about the product because the next entry that we're creating in post is product. We're starting out with prior densities that just from our beliefs that the mean is normally distributed around 178 with a standard deviation of 20. That's approximately, the estimate of what the mu actually is. Meanwhile, the standard deviation we're hypothesizing is equally likely to be anything from 0 to 50. So that's a uniform density. So dnorm post $mu means we're taking the mu value for each row and finding its density for that particular mu in its mu distribution. We're taking the logarithm, and likewise, we're taking the sigma for that row. So to calculate the probability density of the model, we'd be talking about the probability density for the mu times the probability density for the sigma. And if we're using logarithms, the product becomes a sum. So we take the logarithms of both quantities. This post $mu is taking the particular entry in that row for mu and working out how likely is that given our prior beliefs about mu. And it's giving us the height and then the logarithm of that. Likewise, the logarithm of the height of the density for the uniform distribution for the case of sigma, and then those are getting added together. And because we're doing a product overall, we're adding both of those to the log likelihood column to produce the product column, because it's the product of the log likelihood with the prior distribution probability densities. So what that product is giving us is essentially the numerator here. Finally, we come to the last line of the code, and there's more mathematical tricks coming up now. What it says is we're creating another entry in the data frame, post probability. Prob gets assigned the exponential of that product we just found minus the maximum value of that entire column vector. What on earth is that talking about? What's going on here is we're taking advantage of the fact that this whole denominator that we have no idea how to do is nothing but a scaling factor. We're trying to find a distribution. And we know that the density has to work out to be 1. So if we're off by a multiplying constant, then we can figure out how to fix that. The typical way to do this would be to take each value and divide by the sum of all the values to turn them into actual probabilities. Instead, he's doing a different trick. Now, these probability products here. Now, since we've been calculating log likelihoods, you have numbers that are probabilities are numbers between 0 and 1, but densities can have any positive value. So we're taking logarithms of a wide variety of positive numbers, and that's good because you can only take the log of a positive. But what you're going to get is a mix of positive and negative numbers. Now, what do we do with those? What he is doing before the exponential part is he's taking the entire column of the post product and subtracting the largest value. So if you're subtracting the largest value from everything, then that means that your biggest value is now 0 and everything else is negative. So that's a way of guaranteeing we have a bunch of negative numbers. Then if you perform the exponential of that, the exponential of negative numbers are always going to be numbers from 0 to 1. So this was a way of getting it out of logarithms and back into the realm of something you could consider scaled to a probability. Weirdly, it's still not a probability because he hasn't properly normalized it. But for the sampling purposes, you don't actually have to have it normalized. It turns out if you tell R in the rethinking module to sample from a distribution, you can feed it a distribution and it doesn't have to be normalized. It will just normalize it itself as it works. So that's the last sneaky little trick he's doing in this piece of code. That took me a while to work out, so I thought I would share that with you, and hopefully that saves you some grief. Good luck with it. Thanks for watching.